Okay, welcome back to part 2 of the properties of the sun. So I left you with a couple of questions and exercises to have a look at. So I was asking how many basically protons are in the sun. And to look at this, then you already had the mass of the sun, and what you need to do obviously is go away and look up the mass of the proton, and then you just need to divide the two. So here you can see this will be the number of protons. Here's the mass of the sun that we're assuming is pure hydrogen, and here is the mass of the hydrogen atom, if you like, or hydrogen proton, the proton in this case. Okay. And here are the numbers. So 2 × 10⁻³ kilograms is the mass of the sun, as we had in the first part. And here's the mass of a proton. So divide those two numbers, and again, just that gives us 1 × 10⁻57. Okay, so there's an awful lot of protons in the sun, and this will become relevant when we're starting to look at the fuel for how the sun is powered in a second. Okay. So just a point here, a lot of these kind of calculations that we're doing in astrophysics, then, you know, 1 or 2 significant figures is usually plenty. Often we're just looking for an order of magnitude type of estimate. So bear that in mind when you're answering questions. The thing to do is always have a look at the accuracy of the information that is given to you. If the information is given to you, like here, accurate to just 1 significant figure, then quoting the answer to 1 significant figure is the right thing to do. If it's quoted with 2 significant figures, then quote 2 significant figures in your answer. Please don't quote 8 decimal places that your calculator gives you, because that accuracy is not justified by the input information. Okay, so that's a good habit to get into. Okay, so let's now start to look at the energy source of the sun. And for that, we're going to first look at asking the question, well, how long has the sun been shining at its current rate? So the sun is emitting radiative power from its surface. So how long has it been doing that? So that it's basically how long do we think the sun has been around? So that's a bit of a tricky thing to measure, of course. So one sort of indirect way to do that is to ask ourselves about, how long has the whole solar system been around? Okay, so we will, in later parts of the astrophysics course, then we will see that when we think planets and stars, they basically form at the same time. It's all part of the same process. So therefore, it's reasonable to assume that the Earth and all the other planets formed at the same time as the sun. So one way to get a handle on a lower limit to the lifetime of the sun is through our own geological evidence here on the Earth. Okay? And that tells us that the Earth is basically 5 billion years old, give or take. So you can do dating on the Earth through radioactive decay dating of very long half-life elements like uranium, and so the oldest rocks on the Earth are about 5 billion years old. Similarly, the oldest rocks on the Moon that were brought back by the astronauts, same lifetime. Meteorites, same lifetime. So we have good evidence that this is the age of the solar system. So the sun has been shining for at least 5 billion years. Now, here you'll have to take a word of faith, because that's only a lower limit. How long is the sun going to go on for? Okay. So there, we'd have to jump ahead and look at the fact that we do actually understand how stars work quite well. Obviously, we're at the beginning of that process here now in this module. But from stellar evolution theory, that we will learn about a little bit later in this module, but also in much more detail in the second year module on stellar structure and evolution. theories developed there which match all the observational tests for stars as well as we can match them at the moment, tell us that the sun is going to live for a total of 10 billion years. So the sun is basically halfway through its life. Okay. We're going to find this throughout this course, actually, that the sun is a very average star, nothing unusual about it. And so here we've learned already that the star is basically middle-aged. Okay, so if we now take that number, we can work out the total amount of energy that's going to be required to power the sun throughout its entire life. So to do that, we're going to make an assumption that the rate at which the sun is losing energy, the luminosity, okay, so we've already introduced the term luminosity. It's the number of joules per second, number of watts that the sun is radiating from its surface. So let's assume that the sun has been radiating and losing power, losing energy at that rate for its entire lifetime, so that luminosity L has been constant over its entire life. So that is an assumption. Again, it's underpinned by the theory that it's a pretty good approximation, and also geological evidence into the past shows that, you know, the temperature of the Earth and therefore the radiative power of the sun must have been pretty stable over that time. Okay, and so this is a fairly simple formula. All we need is that the total energy is going to be the rate at which energy is lost, so the luminosity here, times the lifetime. So I'm using the symbol tau here to represent this 10 billion year lifetime of the sun. So we just need to put all those numbers in, okay, and make sure we convert everything to SI units. Okay, so here is the luminosity of the sun, 4 times 10 to the 26. So I'm using the just 4 dot 10 to the 26 here, so the dot, it doesn't mean 4.1, okay, so don't get confused there, it's just 4, and the dot is shorthand so that we don't have millions of multiplication signs here. So 4 times 10 to the 26 times the 10 billion years, so this number here, and then multiplied by the number of seconds in a year. So you can easily calculate that. Just take 60 by 60 by 24 by 365 days in a year, and that will give you a number that's about 3 times 10 to the 7. So again, everything to one significant figure, that gives us 10 to the 44 joules of energy is required to keep the sun shining for its entire life. Okay. So that's an awful lot of energy. So where's it coming from is the next question. So, as I'm sure you're aware, the sun is basically a mega sort of nuclear reactor, but it's not a nuclear reactor in the sense of nuclear reactors here on the Earth, which are powered by nuclear fission, which is where you take heavy elements and split them up. The sun is powered by nuclear fusion, where you take light elements, light nuclei, and fuse them together. So how does this occur? Why does it occur in stars and in the core of the sun in particular? Well, again, I'm going to have to quote some numbers at you here. Again, in the second year course on stellar structure, you can kind of prove these numbers to yourself, but for now you'll just have to take it from me. And you might well imagine that the conditions right in the center of the sun are extreme. Okay. And so you have extremely high temperatures. So basically 10 million Kelvin is the temperature in the center of the sun. And also you've got an enormous weight of material pushing down on the center from above, so gravity pulling everything in. And so the pressure of the gas in the center of the sun is incredibly high. So a good point to make here already is that the sun is basically a ball of hydrogen gas, okay? So there are no solid or liquid phases there. The temperatures are too high for those conditions. So everything stays as a gas, more accurately as a plasma, okay? We've already said that everything certainly in the middle part of the sun is ionized, and so you've got this very high density gas there. Okay, so under these conditions, so you've got high temperatures, and high temperatures mean particles are moving around very quickly, okay? And you've got high pressures and high densities. And so that means that the particles, the nuclei, if you like, are packed very closely together. So those are the kind of conditions that you need in order for a nuclear fusion reaction to get going. Okay. So those conditions are so extreme that you can get this kind of reaction going. So this is so we've already said that the sun is mainly made of hydrogen, and in the center of the sun, you've got hydrogen nuclei. So again, just protons flying around at high speed and pushing them together in the high densities. You can get them close enough together that nuclear forces come into play and that the two protons can start to stick together. And in a nutshell, again, there's quite a lot of detail in here that we don't need to concern ourselves with in this module. So for the purposes of this module, the bottom line is that effectively 4 protons have to end up being stuck together, fused, in order to form the next stable nucleus, which is the helium-4 nucleus. So if you look at the periodic table, you know, the next most stable element after hydrogen is helium, and the helium-4 is the stable isotope. Okay. So that's basically what's going on in the middle of the sun. You're taking hydrogen, fusing it together, and forming helium. Now, you see a couple of other symbols on the right-hand side here. So this symbol gamma here is standing for basically gamma rays, if you like, basically photons, basically energy. Okay. So the whole point of this reaction is that it produces energy. Okay. And it's that energy which comes out in the form of high energy gamma rays, which then, you know, basically go into heating the gas. Okay. So these are just photons. So you're producing high energy radiation. So that heats the gas up. And so this all becomes a self-sustaining process in equilibrium. The other symbol here is a Greek nu, and it stands for neutrinos. Okay. So another type of fundamental particle is being formed during these fusion reactions, and these are neutrinos. Okay. So that's a whole story in itself. So from the center of the sun, lots and lots of neutrinos are being formed by these reactions. Again, you can read about that story in the textbooks if you like. It's not part of this module, but you know, we have detected solar neutrinos here on the Earth, and it actually gives us a very good insight into the center of the sun, because neutrinos basically interact extremely weakly with matter and just come streaming straight out of the center of the sun, and we can detect them here on the Earth. Okay. But again, that's not really what we're concerned with in this module. Here, we're now concerned with, okay, so this is the proposition that this reaction can produce the amount of energy required to keep the sun shining. So does that stand up? Okay, so where does the energy come from? Okay, so this is where we, the first mention of many in this course for Einstein. So Einstein told us that matter and energy are equivalent. Okay, and the thing that happens during a fusion reaction is that a small bit of mass disappears and turns into energy. Okay, you'll get to check this for yourself later. So, but for now, if you look up the mass of 4 protons and compare it to the mass of 1 helium-4 nucleus, you see that there's a slight difference. Okay, so AMU here standing for atomic mass units. Okay, so the usual units that you measure nuclear masses in, and so there's a difference. A little bit of mass disappears during the reaction when you fuse 4 of these to form 1 of these. And if you look at this in terms of a percentage, okay, you just take this and divide by 4 basically, then that will shows you that basically 0.7% of the mass, or 0.007 of the mass, is disappearing as a fraction during this reaction. Okay, So that's where the energy is coming from. Okay, so the next question is how much mass is involved in this fusion in the center of the sun? Now, we'll go on to look at the surface temperature of the sun soon, but conditions at the surface of the sun are much, much cooler, much, much less dense. There is no fusion going on the surface of the sun. In fact, you have to go a long, long way down into the sun before the conditions are extreme enough that you can actually get this fusion reaction underway. So it's actually only 10% of the total mass of the sun in the core is where the fusion is going on. So that gives us the total amount of mass of hydrogen, if you like, available. Again, let's just keep assuming the sun is pure hydrogen for the moment. So that allows us to now complete this calculation. So we're going to use Einstein's famous formula of E equals mc squared. Okay. So that's the formula that tells us that energy and mass are equivalent, if you like, and the way to transform between them is to just multiply by the speed of light squared. Now, I've put a delta m in here to remind you that it's the change in mass, okay, like we had up here, that is going into the energy. It's not that 4 protons are totally disappearing, okay, so that's a common mistake that students often do. They think all the hydrogen's disappeared, and therefore that, basically 4 atomic mass units have disappeared. That's not true, okay, so it's only this fraction of the mass that's disappearing. So it's not 100%, it's only 0.7%, okay. So it's really E is delta mc squared. It's a good way to remember that. Okay. So let's put all those numbers in, okay, to the calculation here. So we've got 0.1 here, that's your 10% of the total mass of the sun. We've got this efficiency for the nuclear fusion reaction where you're turning hydrogen into helium of 0.7%. So if we express that as a fraction, it's 0.007. Okay. Here's the total mass of the sun. Okay, so we've got 10% of the total mass of the sun, and then we've got this efficiency factor. So that's giving us the total amount of change in mass, if you like, that's turning into energy. And on the end here, we've just got the speed of light, 3 × 10⁸ meters per second squared. Multiply all that lot together, and hey presto, you get 10 to the 44 joules. Exactly what we needed to explain how the sun can shine at its current luminosity for 10 billion years. So this is why we believe that nuclear fusion is powering the sun. The energy works out. It predicts that the sun will emit neutrinos, which we can detect now these days at the right amount as well. And so everything works very well. We do understand the sun extremely well. Okay, so that's good. We've looked at the lifetime and energy source of the sun and shown that it's nuclear fusion. And just to give you sort of a bit of a picture of what's going on, so what we've been discussing here can be described as the thermonuclear energy core in the sun. So it's right in the center. So this is where you've got the conditions of 10 million Kelvin and a billion atmospheres of pressure. Okay, so only here is where fusion can take place. So it's only in the core of the sun that hydrogen is slowly, it's steadily being turned into helium. Okay, so that's the part we've been talking about here. In the next part of the lecture, we'll start to think about going up towards the surface and how the energy escapes and what we start to see on the surface. Okay. Before we get to that part, we'll a couple of things for you to think about before we move on to the final part of this lecture. So here's a little quiz question, just really to get you thinking about things. So what stops the sun collapsing under its own weight? So you've got 5 different possible answers here. So have a think about that and pick one of them. Again, you don't need to send answers in or anything, just think about it. And we'll discuss this after the break. And again, it'd be good for you to do a little numerical exercise yourself before coming back for the final part of this lecture. So go back and check for yourselves this mass difference between 4 protons and 1 helium-4 nucleus. So you'll need to go and look up some data. If you're a physics student and you've got access to the particular textbook, then you can look it up in there. But basically you can look it up on the web as well, of course, but you need to be accurate, okay? So here you do need to be accurate because you can see that mass difference isn't very much. So you need, probably 5 or 6 significant figures to really show up that mass difference. So find a good source of physical data to look up the mass of these nuclei, and show that the difference between 4 of these and 1 of these is indeed 0.7% of the mass. Okay, so those are the 2 things to think about before you come back after the break, and we'll do the final 3rd part of this lecture.